think we have now collected more or less the relevant terminology that allows us to describe the situation that we have in Gabor analysis in sufficient detail. I will switch more or less from the stepwise mode to the survey mode or so. So essentially, what we need to understand Gabor analysis is, first of all, what are time frequency shifts that we have seen, what are spectrograms. This is, we have a continuous family, and you can think of a Gauss function moving around in time and frequency like a sensor in the score plane, and you would like to know what can I hear at that time, at that frequency, what kind of energy distribution do we have. Moyal tells us if we normalize everything properly, then the total energy in the signal is really spread out in the spectrogram or in the short-term Fourier transform absolute value squared. And we have this notion of Banach-Gelfand triple. Yeah, maybe I should go first to this other slide. I should like to show you this other Banach-Gelfand triple that we have in a moment, but to continue with the Gabor stuff. And now we have the right function spaces that allow us to describe the situation of sampling a spectrogram, rebuilding everything from the sampled spectrogram, expanding functions into non-orthogonal systems in this terminology. So we have a compact terminology, we have the right functional analytic arguments. We have something like the discrete measures as a model case. It was not so symmetric, but it was telling us how to work with weak star convergence and so on. So just before going directly into Gabor analysis and especially dealing with the Fourier transform, I wanted to remind you that we have already in the literature a number of Gelfand triples. And the first one that is the most well-known is the Schwarz-Gelfand triple, and that's why I'm using this terminology. The Schwarz-Gelfand triple, of course, is very important because you have the Schwarz space of rapidly decreasing function, which I have symbolized by this multi-semi-norm topological vector space, which is nuclear and Fréchet, sitting inside the Hilbert space, and the dual space is containing it. So nice functions are clearly even L2 functions, even polynomials are in the tempo distributions, and Dirac's, derivative of Dirac's are in this big space. So you should think of this much bigger than this one, because if you align them, they are sitting inside each other. I will tell you and promote this one, how you can use it and why it's useful in the context of Fourier analysis. And I will show you mostly in Gabor analysis, but I could also give a talk, so to say, it's useful for classical Fourier analysis, just because when you take L1 and you go to the Fourier transform domain, you are a little bit outside of S0 on the range, or outside of L1. So how do you get back to this? We have seen you're applying summability. And actually what we're doing, we're pulling everything into S0. An element from the Fourier algebra will be multiplied with a Gauss function. Well, very flat, but decaying. The Gauss function is S0. Pointwise multiplication draws us into S0. So somehow we're saying what we do when we prove the inversion theorem, there's an easy trick to get from the Fourier transform, which may have bad decay, into S0, and then we go back. And then we lift and go to the limit. So it's just this game of interior objects are nice objects, and you deal with them in a good way, and then you take limits in the appropriate norm. This is standard Banach situation game. Again, this is not a Banach space. This is, of course, a Banach space with a dual space. The prototype of these spaces is L1, L2, and L infinity. So here L infinity is shown as unit circle, unit ball. All the sequences with maximal coordinates in R2 look like the green square. The L1 norm unit is like this, and you have L1 and L2 and L infinity. I want to mention, and without maybe going into the details because we may not have enough time, so if there's time I will tell you more about Wilson bases, but there are two important remarks. Wilson bases are orthonormal bases for function spaces which map this in a unitary way. So my one formulation would be there's a unitary Banach-Gelfand triple isomorphism between the prototypical sequence spaces L1, L2, L infinity, and these spaces. In other words, some time ago, or I think in 92 or so, Ingrid Obsché and two of her co-workers were reading some paper by an applied person, and he was saying, well, I think it would be nice to make out of time frequency localized building block some orthonormal basis, and intuitively it could be like this, and he was giving some hand-waving arguments, and that's why it's called Wilson basis, to show that one could make time frequency basis. Now, Balian-Low theorem, which I may mention later, is you cannot have a Gabor system which is an orthonormal basis. So it's not just that Gabor was not finding it, it's just impossible if you really do time frequency shifts. What the amazing thing is, you can combine things with equal frequencies of positive and negative ones and get out of a Gabor system of redundancy 2, by gluing together the pairwise, roughly speaking, you can make an orthonormal basis. And if you see a building block, it will be a cosine or sine with some shift factor. The trick is to put the shift factor in the right way. So essentially you align one column like cosine pairs and next like sine, and cosine and sine. And so in MATLAB, if I have two n vectors which form a tight frame, which I can do, it's not so difficult, and I pair them together, I get a Wilson basis which has exactly n elements, and by magic tricks it's orthogonal, so it's an orthonormal basis. So if you think this can be done in the infinite dimensional situation, we have the Hilbert space and the orthonormal basis. And then you can ask, well, I can take the functions which have absolutely convergent Fourier series. The building blocks are nice, so it will be clearly in the Wiener algebra, and the nice thing is it is in a zero. The other thing is I can construct nowadays a lot of Wilson bases. So do we have each time a new orthonormal, a new space of absolutely convergent objects? No, they're always the same, so it's always the zero space. Just by analogy, we have tested in the course, if you take a rectangular function, you can also say this is a nice orthonormal system. You shift it around, you multiply it with pure frequencies, it's an orthonormal system. If I take this rectangular function and move it by 1 pixel in the infinite case, and I look at the absolutely convergent things, it's a new space. Next one, a new space. For each orthonormal system, which is kind of like this, but the building blocks are not in the nice space. They're not good functions. Then you get different things. That's why, yes, you have a lot of isomorphisms, but the general idea is all these building blocks are very nicely concentrated in time frequency, and that's very close to Gabor analysis.
Isn't the case that this inner and outer space are always algebras?
That's a good question. No, I mean, I can tell you in this case. In this case, we know already actually. S0 is an algebra for multiplication and because it's Fourier invariant for convolution. S0 prime is neither for convolution nor pointwise multiplication because you cannot, I mean, you have the deltas in this large set, so you can take the pointwise square of a delta, or you cannot convolve constant 1 with constant 1. So I think this is a very specific structure. That's an interesting comment. Yeah, it's a specific structure of the sequence space, which does not transfer into this, at least not in the natural way. I mean, for me, the objects here have a natural structure. You can have a natural multiplication and convolution. Of course, you can say, if somebody is giving me, I mean, you can transfer structure. You give me two distributions. I look at their coefficients. I do a pointwise multiplication.
But when you say that that is unitarily equivalent to this, it means you can define multiplication there also.
Yeah, I think you can take the structure that you have here, and because it's a bijection at all levels, you can transfer the structure. So I'm not saying that it's not possible. The question is, what kind of multiplication in the sense of pointwise do you have? And it's certainly, it must be different from the usual concept of multiplication. Of course, you can say, I have pointwise multiplication of coefficients here, and that must be something that maps a 0 into a 0 in an associative way. I really don't know what it means. I would guess that this is at least dependent on the basis, and then it's not so interesting, because you have a manipulation that changes each time you change the basis. So, I mean, you can also say, I can turn R3 into an algebra by taking two vectors, but viewing their coordinates as functions on the cyclic group of order 3. I have never studied it. It can give some surprising results, but it's not what we are looking at least. That's my comment. And the last thing, people in PDE, of course, use Sobolev spaces a lot. And they would say, that the elliptic partial differential equations are so interesting because they map a Sobolev space of order +1, so 1 times differentiable, losing 2 degrees of smoothness into Sobolev space of order -1, but that's the dual space. Both of them are Hilbert spaces. Both of them are isomorphic to L2. So somehow a Laplace operator is more or less in these coordinates an invertible operator, and you have uniqueness of solutions or so. Now I have this picture. You can rotate it by 90 degrees, meaning going to the Fourier transform side. Weighted L2 spaces are inside L2. If the weight is growing, you have a weighted space inside L2. And the dual space is the L2 space with respect to the inverse of the weight. So in that case, this you could call this a Hilbert space Gelfand triple, but normally, yeah, well, for PDE, even the Hilbert space structure is used very much. For us, it will be interesting to have only this situation, and among others, kind of pre-announcement. These spaces are also very important for their kernel theorem, so that you represent linear mappings from Schwartz to tempo distributions by some two-dimensional distributions. And usually it's assigned to the property of being a nuclear Fréchet space. So nuclear kernel, that's more or less the same way in Latin. And therefore, very often you read statements like, if you don't have nuclear spaces, there's no chance for a kernel theorem. But that's one of the points that I definitely will try to do tomorrow. So we have a kernel theorem, which is the analogy, the continuous analog of a matrix representation theorem. But before doing this, I wanted to mention one more thing. So without showing these Wilson bases, but they look like Gabor building blocks. This isomorphism is nice and abstract, so Wilson bases are nice. But you may have heard that this year the Nobel Prize for Physics was given to the team, the huge team of people who were detecting the gravitational waves. So one way of explaining what was going on is Einstein 100 years ago was predicting that you have two black holes, so clearly objects which are very mass intensive and attract each other. They would do something like this and it would start curling up. That will influence space. So there will be a gravitational wave will change space structure a little bit. You know, if the gravitation is changing, then the propagation of light and so is changing a little bit. And so 100 years later, people were successful in measuring with some laser devices, very huge devices or so, with very sensitive things, the effect of some gravitational waves. Somebody was saying this.
Gravitational waves between the black hole collision also.
Yeah, this is the kind of, it comes from black hole collision, and it's away, I don't know, millions of years. So it must have happened very long ago, and it was not clear whether one would ever be able to observe it. What one knew, however, is that the structure of the signal that we were looking for, and essentially it's kind of a noisy environment, and we agree that if you say some keyword, then I would say, oh, there was something going on, yeah? So it's a noisy room or so, all of you would talk or so, and I should find out if somebody, I don't know who and what exactly, but say something which sounds like what I'm waiting for. And then I would say, oh, this word has been said, and now I have to try to find out what the parameters are. So how big were the black holes, how much mass was lost, so how much energy was evaporating according to Einstein or so. That's what they really have done or so. So the signal was a so-called frequency chirp, which in time frequency would be something going up. So I tried to imitate it as so very short, very slow. If you, let's say we were kind of, we have the monkeys here. If they would have some, or some of these animals would have some particular warning, then we all would have to hide or so. But it's a noisy environment. So the point is, we have the time frequency plane full of information, but we look for something which has a particular shape. And they were having already the idea one has to use spectrograms in time frequency analysis, but they had two strategies. One was to say, we think we compute and pre-compute a certain number of templates. I'm not sure if the order is right, but at least 2,500, maybe 25,000. Let's say 2,500 templates that they said, well, this is plausible, that could occur. And the other alternative strategy was to use 14 Wilson bases. And the first observation, which is of course the most important because now then they knew it, it was September 16, I think, was detected by the Wilson bases. Why was it detected by the Wilson bases? So the coefficients looked like this, and they were verifying that two independent observations at the same time with the right delay. So you can imagine it propagates and there is microseconds difference, and that can be explained. So it was not random, and they verified it. So they were using the Wilson Basin, and they found it because the range of the event was out of the range of parameters that they were expecting. So to say, the event was bigger than they thought it could be observed or could happen. And of course, for the Wilson basis, it's to find something big is easier than something small. But if you look for something small and you get something bigger, you don't think it correlates well. So that was why this strategy was, I think, successful in the first time. And I think the second time they were enlarging this, and the second was then you found with the other strategy. As far as I know, they have now 3 or maybe even more hits, but they've published 3. And it's a huge thing, and somehow it's not far away from time frequency analysis. That's why I wanted to mention it at least. I will mention it in the talk on Monday also. Okay, so
That is positive Sobolev space, L2 and negative Sobolev space.
yeah, that would be the 2 Sobolev spaces, and they are under Fourier transform isometric to weighted L2 spaces, of course. Now, I would like to mention two things and describe mostly now how can we take a new look at the Fourier transform, which you all have understood, by looking at these new triples of spaces or so. The first thing is we have seen that the S0 space is invariant under the Fourier transform, therefore f hat is well defined, and if you give me a linear functional sigma in S0 prime, I can apply it to this. This makes a bounded continuous linear functional. So for every sigma in S0 prime, composing it with the isomorphism Fourier transform will give a new one. So one has to verify that this is well defined. It's a linear mapping. In our case, we have seen in the S0 norm, and we have not seen, I have mentioned it and I have to repeat the claim. The S0 norm is isometric Fourier invariant, because by Plancherel, it's really, maybe I'll do it next time, 3 lines or so. They're applying the Fourier transform rule using Plancherel a little bit, and the invariance properties is rotating the spectrogram. And everybody agrees rotating the spectrogram is harmless. It doesn't change the L1 norm of the spectrogram. Okay, so because of this invariance, also the dual one is okay. But every adjoint operator, I should actually say now we are having not a Hilbert space pairing, but a Banach space pairing, is weak star convergent, continuous. It's just because if you have something that is understood by acting on the operators, if you apply an operator to something which is convergent, then it's okay, and then you rewrite it back into the weak star terminology. So this is a thing which is some operator which maps functionals into functionals. Now you can say we have already inside the big space nice test functions. So it would be a disaster to call, we shouldn't call it Fourier transform, it wasn't the same at the ordinary level. So we have this commutative diagram, or I call it consistency principle. Take the thing, move it over to the Fourier transform as a function. If it's a nice function, you can take that target as a distribution, or make a distribution, apply the new principle, and try to find out. And of course, it's more or less the fundamental relation, or somehow it's the same as Plancherel theorem that tells you, no, there's no problem. This is really the same, and it's actually how it is made. So you try, say, that's very often the rule that you can find. How can I describe a new operator on my set of distribution? And then you rewrite it by saying what that ordinary function viewed as a distribution would do on a function. And then you use this as a definition. So for example, we have mentioned already we can do the ST row operator on the measures. And now if you would say I have a function and then I compress it, you would say I substitute and I replace, I don't know, x by x divided by rho or something like this, and transform and say, and you come out, it's the same as integrating your original undilated function on d rho. That's why I'm using both of these operators. So my definition was simply ST row of a functional is the functional applied to d rho of the function, and vice versa. If I want to do d rho, I have this, and I was indicating in some argument that ST row is mass preserving and support moving. So a delta not changing amplitude will be moving. D rho is changing the amplitude because if you give me a Dirac comb which is well spread, and I concentrate it. I would like to have Riemannian sums, and in these Riemann sums, the length of the interval is used as a compensation for higher and higher sampling. So it's sometimes really good. The Dirac sums go to the integral, to the Lebesgue integral. Oh, that's good, because if we are saying the Dirac combs under d rho go to constant 1, it is more or less the same as if I take the Dirac comb with st rho and stretch it. And I told you this story. What is my picture of y is st rho of Shah distribution? That's my name for the Dirac comb. With rho going to infinity, why is this the Dirac at 0? You have this Dirac comb. I'm a test function more or less sitting here. And now you start making rho larger and larger. So the Diracs are moving to infinity. At the end I'm here and saying, well, only the guy in the middle is here and the rest doesn't act on me as a test function. So in that sense, it's st rho Shah goes to this in the time side to delta 0 must go to Dirac 0. But these are discrete measures. There's not continuous functions which are going uniformly over compact sets. So that kind of understanding is very important. Okay, so maybe already here we can say, to go into the very general terminology, one benefit that we can do is, which actually engineers do a lot, they say sampling corresponds to periodization. But I'm trying to make it a little bit more precise. I can say, well, if you give me, it has to be a lattice, you give me a subgroup, a discrete subgroup of a locally compact
How do we
abelian.
read that symbol?
Pardon?
How do we read that symbol?
Okay, yeah, we read it as Shah. Shah with S-H-R, Shah. Yeah? I must say this, some people call it Dirac comb and make errors. That's one of the reasons why we do it. Actually, in LaTeX, it's not so easy because it has to be two rectangular U's glued together so that they overlap nicely. So it's sometimes tricky. Sometimes I have a problem. They are separated and it's not good. Okay, now, but this Shah, my understanding was, I don't know, I have no detailed knowledge of the Russian alphabet. But you may remember there was the crisis when Kennedy, with the Cuba crisis or so. So there the minister president of Russia was Khrushchev. I think this sh, which is represented by this. So it's a letter in the Russian alphabet also, but I think it should symbolize a part of the Dirac comb, and you would say stem, a unit vector which is spread out at equidistant things. That's what you have. Okay, so Shah, if you give me some set, I would just say, you give me the points in the plane, for example, and we say now I can evaluate. Sampling theory would say I can have the Diracs, and so essentially one way was people would say, okay, you give me a measurement at this point, and this was the value, at this point, and this was the value. And I would say, you give me a continuous function, and we multiply the discrete measure, which is a well-defined object, with a continuous function. In the same way as we have h times mu until now, bounded continuous function with a measure and so. What is it? Is the result. So what you get is a sum of Diracs where the amplitudes are there. What is the Dirac telling you? That's where the value is. What is the amplitude telling you? What the data are at this point. So it's just another way of looking at it. The good thing is, whereas if you are having now a list, an indexed list of positions and values, and then somebody has to say, well, I'm doing now a linear combination. I'm putting a Gauss function of this amplitude here and a Gauss function of this value here. I would say, no, and then in MATLAB we really do it in this way. We're saying we have this unit vector sitting at the positions, and continuously written you have Diracs. And then I convolve this discrete measure with some smooth function. And for example, if you would have cubic spline function, I would say, well, you would like to place the cubic splines at the lattice points. So I would produce a spline function not by putting 1 and 1 and 1 and 1, but I do what is called a semi-discrete convolution. I would say I take the sum of the Dirac. The amplitude here should be this. I put the Dirac here and this and this. I take this sequence with a lot of zeros and ones, take the FFT, and I multiply with the FFT of my B-spline, and then take an inverse Fourier transform. Then even if the number of points increase or so, it's not slower because I need three Fourier transform each time. So that's a fast way of really also practically to create some curves and to do some computation. Okay, so that's one of the reasons why we do it. So here it's the idea this is a subgroup. Now, again, you can get an idea what happens by doing everything in MATLAB in a discrete setting. I was mentioning in the session in the morning. If you take the Fourier transform and you apply it, you get another Shah distribution, as I call it, but on the orthogonal lattice. Now, what is the orthogonal lattice? By definition, abstract definition is you take all the, I call it now pure frequencies, all the characters which have the trivial action on my lattice here. What does it mean in practice? You have some lattice point, maybe in the plane, a lattice, hexagonal lattice or so. Now you're saying there are a lot of plane waves. But there are some plane waves with appropriate direction and appropriate amplitude or so, which happen to be, I mean, the tip of the wave, you have exactly once at all these lattice points. So you can easily imagine to draw pictures of how these things have to be. There is some kind of minimal frequency that you need so that the one wave is going up, and where you have the generator, it's going. And then you take others which are more fine, but they also go back. So somehow it's clear that it must be a discrete set or so. And that's actually, these pure frequencies make another lattice. And this is called the orthogonal lattice. Why is it called the orthogonal lattice? It's called the orthogonal lattice because if you think what are the plane waves which are constant one on the x-axis, then you find out all the waves which come in vertical, so which have a normal vector along the y-axis. If you have this point here, for example, I would say, okay, it's distance 3. That means I have plane waves, and they have 3 oscillations if you think of them in that direction. If you are at 1/2, then you have half an oscillation. Well, it means it needs two units to do this. So I have constant 1 on my axis. It goes down, and the next wave is at 2. But it doesn't matter. They are all constant 1. So all the pure plane waves which are constant 1 on the main axis are the ones which have a wave number description by a normal vector along the y-axis. And you can do this in the same way, rotate around, and you see that this is okay. What is not clear is if you do it in a discrete way, you can say, well, what if you have an integer lattice? Then you have to play around with exponential functions. So you would like to ask, what are the values s, so that e to the 2 pi, no, the vectors s, s1, s2, such that e to the 2 pi I, so then I have the set d case, e to the 2 pi s1 with k1 plus s2 k2 equals 1 for all pairs k1, k2, which are integer numbers. And then you easily find out this is only possible if s1 and s2 are integers. Because clearly, if somebody is giving you integer vectors only, the scalar product will be an integer. And if you write e to the 2 pi with an integer, it will be 1. So that they are in the pot, and if you are not in the, it's not working. So the orthogonal lattice, and that's the most important thing which gives us Poisson's formula again in a different form, is if this is set d and we have our normalization, this will be set d, and this constant will be the area of the fundamental domain, which will be 1 again. So then it will be exactly the Poisson formula which tells you if this is the integer lattice, this is the integer lattice as well. So the important message is even unbounded measures like constant 1, pure frequencies, now they have a Fourier transform. Good exercise. What is the Fourier transform of a pure frequency? You can imagine the musician would say, I hear 44 hertz, and it's some amplitude, and you expect it will be some delta. And you only have to check, and I think that's probably what you get out. If you say pure frequency chi with label s, it should be delta s. Because we have seen in the opposite direction, if you put in a delta s, it has an inverse Fourier transform that's going, a forward Fourier transform, forward Fourier transform going into chi s. So if I go in the opposite direction, I have a different sign, so I think it's plausible. Pure frequencies with label s go to deltas. Okay, so I think that's very good that we have mentioned this, because now I can try to give you, so to say, my perspective on what the Fourier transform is. So you have seen the Fourier transform starts as an integral transform from L1 to L1. You extend it in a suitable way to L2 to L2. It's unitary at that level. I told you now you can restrict it to S0, and somehow I tried to tell you forget about L1 for a little while and just concentrate on S0. These are nice functions where you can test with the Riemann integral whether it's in the space, and if it's in the space, also the Fourier transform is in the space, can be computed using Riemann integrals. On the Fourier transform side, you don't have to worry about inversion. It's a continuous function on the time side, integrable on the Fourier transform side. Riemann integrals help you to come back. So we have a very nice space like the Schwartz space, but actually much bigger. Piecewise linear functions are in the space, for example. And so we have these three layers. Just more or less I'm spelling out once more what that is a unitary Banach-Gelfand triple isomorphism. S0 is mapped into S0. It's isomorphic, actually isometric if we choose our Gaussian norm. It's isometric and one-to-one, therefore scalar product preserving, therefore unitary. This is Plancherel in one package. And it's also bounded and as well as weak star continuous. Therefore we can claim it's a Banach-Gelfand triple isomorphism. Now, maybe I'm just talk about this now. The second statement is, if we look at again at the FFT or the DFT, I mean, implementation is not so important now. The discrete Fourier transform, people would say it's going from Cn to Cn. You plug in vectors of length n, you get vectors of length n, and it's unitary. How can you describe it to people who have an idea about what an orthonormal system is discussed in linear algebra? You say it's a change of basis. We change from one basis to another one. And we have a lot of troubles, and I really try to read nowadays all the possible books about engineering explanations, what the Fourier transform is or so. Very often you come into these things that you get, okay, the sequence of deltas or the continuous family is like a continuous orthonormal basis. People have learned now a lot about frame theory, and they start to discuss continuous frames. Actually, this is where the whole thing comes from. Coherent states were a way of continuously writing the inversion formula, and then the question was, can you discretize it? And for a long time it was clear, yes, it's Riemann in sums. We have not a big error because Riemann in sums are very close to integrals. It was really an important development to say Gabor analysis was telling us you can make it perfect. So there's an error, but by taking dual windows, everything is much better. So that's the big difference. So then for a long time people were saying discrete frames are very important, very useful. But at the end it's an isomorphism between an abstract Hilbert space and the sequence space. Okay, we don't understand, not only understand sequence spaces, but maybe continuous L2 spaces, continuous weighted L2 spaces or so. And suddenly, well, just take the diagram and exchange the role of Hilbert space and L2 by more general things. So I would say most of the concepts about continuous frames is just somebody saying, I have not just an abstract Hilbert space, but a weighted, some measure on some measurable space, which makes a Hilbert space, and embedding from my abstract object into this is something concrete. And therefore, I have something like a mapping with an adjoint mapping, and I compose it, and I get something like a continuous frame operator, all these things. That works quite well if you follow the rules, so to say, of functional analysis and do everything in the Hilbert space setting. But it is not suitable to discuss the properties of the Diracs. The Diracs are not in the Hilbert space. So somehow, the other way was I was telling you take the Fourier inversion theorem. You're saying, well, the Fourier inversion theorem is something like a continuous orthonormal system. You take these pure frequencies. They're so nice. We know they are an orthonormal system in the discrete setting. Now, for non-periodic functions, we need a continuous family. Okay, so we take, for this continuously thought as an continuous orthonormal system, we take the scalar products. Okay, that's great. We know that this is the Fourier transform. And then we glue it together, but the building blocks are not in the Hilbert space. So how can you claim that it's an orthonormal system? And then somehow, yes, you take two Diracs, somehow you smooth them, and these functions are orthogonal, so probably you can go to the limit. Yeah, that's okay. Somehow one Dirac doesn't have to do anything else with the other one, but somehow it's a nasty trick. And especially, why is then a scalar product of a delta at zero with itself well defined, and why should that give a delta function or so? That's where people start to wave hands and make some plausibility, and I think it's kind of, one should avoid it. one should say you can understand everything at the level of pairs of spaces, and you move around, and then you take limits. And for me, these manipulations, again, if you would say the system of pure frequencies is a continuous orthonormal system, or the system of Dirac's is a basis for the functions, then you're talking about the shifting properties of the Dirac delta. So they write a formal integral and say the function is, we say, delta 0 convolved with f. And in my notes I was saying, okay, delta 0 convolved with anything is shift by 0. That's a triviality, that if you don't shift a function, that you get the function back. So in that sense, for me, that's well defined. Not the integral, but the interpretation. If you tell me a function is a collection of all the values, you prefer to write it, each value is a sampling value, therefore if you multiply f with the delta at x, I'm getting a value at the points. And if you tell me all these values, a complete list, continuous list, and put them together and you write this as an integral because you like integrals, then I have also no objection or so. But to use it as a formal machinery is for me exactly the same thing as saying, well, now let's discuss how we can compute pi square. You know, pi is an infinite periodic thing. We're having a philosophical discussion, maybe, so to say, God is able to multiply even infinite numbers. Actually, it's true, it's really. And then we're discussing whether in this multiplication of infinite numbers we can do certain things. I think it's irrelevant. We know that there is a system of numbers which allows us to describe the wrapping up of a function of a rope on a circle. And if we make the rope long and longer, at some point it will close the circle. And we can observe that by dilation, this is true for every circle. And we have the length of the circle is 2 pi times the radius or so. So there must be some real number. And if we describe it in a decimal system, if we need to multiply inverted or whatever, we can take arbitrary precisions and we can compute with arbitrary precision. But we never do the actual infinite thing. We try to approximate with things that we can control, and then we go to the limit. And that's, I think, what functional analysis is telling us. To deal with the infinite without philosophical statements, but having a clear view what the recipe is. And once you have done it 20 times, you're of course learning that this is something real for you. I mean, real in the sense of you don't think that's just a symbol for an infinitesimal and I should do this and this. No, you really write pi times pi squared and do computation. Then when it's e to the 2 pi I, you don't say, oh, irrational number with a complex exponential, terrible. No, you replace it by 1, and it's justified. It's justified, but not as something where you continue playing with the symbols. And I think that's important. Now we have seen that there were a lot of Banach-Gelfand triples already in the literature, and I would like to point out that one very classical Banach-Gelfand triple is already occurring in classical Fourier analysis, and again Wiener is coming into the game. So my interpretation, it's really kind of a homemade historical comment now, is that Norbert Wiener, at the time of where they had understood that in L2 you have an orthonormal basis and you can describe convergence, did not know, because it was only verified by Leonard Carlson in 72, I think, or so, in the early 70s, that the partial sum of a Fourier series for an L2 functions are almost everywhere convergent. That was not known at the time of Wiener. It was known, however, from the results of Kolmogorov, I think in around 1926 to 1930 or so, or really at the time when Wiener was developing some of his theories, that you can have L1 functions, so we would say correct domain for the Fourier transform, where the Fourier series was not only convergent in countably many points, but even everywhere. So it's a complete scandal. I mean, I learned semester number 1, Fourier series, a series is a sequence where the partial sums are convergence. Semester number 3, I was exposed to Fourier series, and I was told, no, you shouldn't take the Fourier series as a series. You should not truncate it and take more and more terms. Nowadays, I think, yes, no, the Fourier transform is a nice mapping. It maps certain object into other objects. So it happens to map periodic functions into sequence spaces. And the way how to come back through series is kind of the lucky case where no problem occurs. And nowadays, of course, I'm saying, well, I can do all these things on every locally compact group. So clear enough, if I do everything on a finite group, we're talking about Cn. It's just L1 of Cn, it's L2 of Cn, it's L infinity of Cn, and everything is convergence in coordinate-wise sense is weak star convergence, is norm convergence. So everything is glued together. Next step, we go to the torus, and suddenly these things start to go away. And we find out, well, there's a small space, a nice space. S0, what is S0 of the torus? So take the compact group, think of a partition of unity in pieces which are of equal size, but compactly supported. Well, constant 1 is a nice partition of unity. It consists of one element, it is compactly supported. So to say that then locally I have something which is having an integrable Fourier transform, nothing else but saying I have a Fourier sequence in L1. So I can describe this kind of almost trivial Banach-Gelfand triple, but the viewpoint is important, as L2 is a nice space, it's a Hilbert space. The pure frequencies we learn, we check the orthogonality relationship, we take Weierstrass theorem to show that they are able to approximate arbitrary continuous functions. Therefore, because of density in L2, arbitrary L2 function can be approximated. So it's an orthonormal system and it's complete because nothing is orthogonal to them. So it must be a basis. So we have a unitary mapping from L2 of the torus into the L2 sequence space. And it's a very important, very useful orthonormal basis. So maybe we take the copy of L1 of our prototypical thing and ask what are the functions that have L1 Fourier coefficients. And that's exactly Wiener's space. He's called A of t or so. It's the absolutely convergent Fourier series. And I would say my explanation of when should you try S0, whenever you are trying to take good functions. Not too good because then the space would be too small, but good so that normal problems don't arise. Poisson formula is okay, inversion formula is okay, many other things are okay. So if you do it on the torus, you get A of u, absolutely convergent Fourier series. The uniformity of the Fourier series conversion is fine and everything is okay. So you can even do a discrete version of Poisson formula. Now then people doing functional analysis, at some point they realized now we have to look at this space and we look at the dual space. So clear enough, the absolutely convergent Fourier series are dense in this. You could say it's clear because L1 is dense in L2, but you take them as continuous periodic function having absolutely convergent Fourier series with L1 norm of the coefficients, and you say they're inside L2 of the torus. And you take the functionals, and because they're dense, every functional on the big space is a functional in a small space. You can distinguish different ones in the different, so it's an embedding. So the dual space of A of t is some space of abstract linear functionals, but it must contain the dual of the continuous function, of course, which is inside, the A of t space is inside the continuous function, also dense here. Therefore, you give it a name and they called it pseudo measures. They are a little bit more general than ordinary measures. And at some point, distribution theory came and said, well, we can even define the Fourier coefficients of a pseudo measure because a pure frequency is a smooth function. So you can pair this functional with this test function. And so you have a Fourier transform. What can you say about this Fourier transform? Oh, it's L infinity. So the pseudo measures, by definition, you could say this is all the periodic distributions, tempered distributions if you want, which are having bounded coefficients, or you could say somebody is making a Dirac comp on the Fourier transform side, on the integer lattice, with amplitudes which are in L infinity. So it doesn't have to go down, but it can phase factor amplitudes or so. And if you take the distributional Fourier transform, you will get the periodic distributions. And which one do you get? Exactly the ones that can be interpreted as dual things. So for me, it's just another way of saying, well, if you have good enough information about this triple on both sides, then you can establish it from whatever level you want to have. So most of the time at the beginning we're saying the Hilbert space is clear, Plancherel is clear. Oh, we find something interesting below, which happens to be L1 that was for a long time. I had S0 for many years, and I had some abstract argument why it must be isomorphic, but by some unknown isomorphism. Now we have Wilson basis, local Fourier basis, and they can all be used to make an isomorphism. And then, of course, by duality, the functionals have a representation in the same system with boundedness. And the sums are not always norm convergence, but they are certainly weak star convergence. Now,
One question.
yeah, please.
Instead of torus, if you take a non-compact group, for example, an R, there we cannot say that A of G, P of G with L2 of G will not give a Griffin tuple, no? Because
No.
A of G
Yeah,
is not
no,
contained in L2
no.
of G, right?
I mean, that's a very important, a good comment in the sense that it reminds me that I should mention something. We have so much trouble with the LP spaces in terms of inclusions, because if you give me two LP parameters, they are not included in each other. We have seen it a lot with L1 and L2 or so. Why? Well, in one direction you have on the torus or on the interval you have inclusion in one direction. A bounded function is square integrable, is integrable. If you go globally, a sequence which is summable, is square summable, is bounded. And you have strict inclusion at each level. So if you want a counterexample in one direction, I choose, let's say, step functions or smooth cubic B-splines with LP coefficients which are not in the space. If I do it in the opposite direction, I take functions which cusps. So more or less I take a function on the torus, glue it on, and make it like this. So amalgam spaces allow me to separate it. Now, when people, and there's a lot of literature, I learned about A of G, the so-called Fourier algebra on groups, by saying, well, one has to take the Fourier image of L1, so what I call FL1. So very often it's called A.
Okay.
And the pointwise multipliers are then the role of the measures, so that they're kind of the Fourier transform of the measures. That's the classical abelian situation. And Aymar was able to characterize this even for long non-compact groups or so.
Yeah,
And
I now understand. Even for amenable groups and other things,
yes,
that is
exactly.
how this
Yeah, you can do it.
Yeah.
But then you can ask what are the properties of these spaces. Maybe without searching for the slides, I can tell you the following. If you restrict a function, well, first of all, we have seen the domain of the inversion theorem is nice. If you take the Fourier, I can take a zero, I can take the Wien algebra and its Fourier transform, or I can, at that time, I would say, I have L1, I have the Fourier algebra, so I make a nice Fourier invariant space, which is also defined on arbitrary locally compacted groups, the intersection of L1 with the Fourier algebra. This is nice because I can do it on any group, because there's always a dual group, and it's under the abstract group theoretic Fourier transform mapped into each other. But then I can say, well, if I have any category, I have the sub-object. So I have subgroups, I have quotients, and so. So what can I say if you give me a subgroup? So now let's just take the plane. We have a function which is integrable on the plane and which is in the Fourier algebra. And now I restrict in two-dimensional space, R2. Now I try to restrict it. And then I can ask, well, is the restriction in the Fourier algebra? And then I have to remember, this is Weil's theorem more or less, that restricting on the time side, I would say I'm multiplying pointwise with a Dirac, with a delta times a tensor, sorry, constant 1 with a delta in this. But I can say it's a distribution integration of a test function of two variables along a line is a linear functional, and this is represented by some unbounded measure. What is the same on the Fourier transform side? Well, instead of integrating, instead of multiplying, it's convolving. But the orthogonal group of something sitting here is in the y direction. So the measure is the Lebesgue measure sitting on the y-axis. And what does it mean to convolve with this? I mean, I have to take all the shifted versions of this and integrate over this. So you would say, okay, he's saying, I have a function in the Fourier algebra on the time side, means I have a function in L1 on the frequency side. And now he's applying Fubini to integrate along the y-axis. That's not a problem. I can use Fubini to say the integral over R2 now on this side is just integrate first in the y direction, and then if what you get is integrable in the frequency in the x direction. So the L1 of the function that you get by making it periodic in that direction or constant in that direction actually, because it's integrable is fine. So Fourier algebra is good with respect to restriction. Now I'm saying, well, now I have a function which happens to be integrable. Will the restriction also be integrable? And there you are in problem, because you can have something where maybe you have small area, I'm thinking of a profile like a triangular function or so. And the area of the triangular function, if I take it as a function of two variables, is harmless. But as I go along the axis, I make the triangle smaller and smaller. So the area is 1 or is decaying in some way. But the restriction operator takes these values which happen to occur on small areas. So the integral is small because the basis is small, not because the values are small. So it's very easy to find a function which is in L1 integrable and you restrict it to a subgroup and it's not good. Or probably you could take a lattice in the same way. If you take the lattice, it's again in the Fourier algebra, so it's having an absolutely convergent Fourier series expansion. No, it's giving an L1 function on the torus on the other side because you have L1 coefficients, but the L1 property is lost. So you have samples which happen to be large, but it's not okay. So in that sense, you can have the problem with restriction, and if you change this on the Fourier transform side, the equivalent problems, you're losing the A of G property when you take quotients. So therefore, S0 is having these nice properties, and maybe now, because we're near the, well, not too much time, but I can mention this, and you will see the slides next time. You can ask the question, now that I claim that I can do for every locally compact abelian group, I can produce this space. It's a kind of functor, so we have this category of all these possible locally compact abelian groups. We know what the mappings are, the homomorphisms, and you can have isomorphisms. And what does it mean that two groups are isomorphic? Well, they are practically the same. Now, I would say take the plane and take the rotated plane. That's another copy of the plane or so. Now I'm taking S0 with this coordinate system or with this coordinate system. Is it the same? So suddenly you can say, you can play it back. Well, if somebody is giving an automorphism of the group, something like stretching or a rotation or so, is this leaving the space invariant? So that's really a nice, harmless question. I will do it only because it's easy to explain without formulas or so. I give you the example of the effect of, let's say, time compression. So we have to think of a signal which is an audio signal. And I'm telling you, think of a tape recorder or an old shellac or so, and you play it and you have a piece of music or so. But then you play the wrong speed, so you play the higher speed. So out of what I'm saying now, you will have a twice the speed means every pure frequency is replaced by the double frequency. So you will see it's, well, S0 goes to 0. Compressing in time means means raising in frequency or so. If you take a whole picture of time frequency, it's dimension 1 stays dimension 1. You have now something which is half as broad, but it's twice as big. So then you can imagine, well, what happens if I take the spectrogram and it's integrable, and I do this time stretching? Well, what I'm doing more or less, I'm compressing in time, but in the same time I'm stretching in frequency, and the error is not changing anymore. The other thing that may happen if you really write the details or so is, of course, I try to really take the spectrogram and modify the spectrogram so that you will say, well, then you are using not the Gauss function, which is Fourier invariant, but you use a compressed Gauss function, which clearly has a broader support in the frequency domain. So we come to one other question, which is also very important in the characterization of this zero space. What if I don't use the Gauss function, but another Gauss function? What if I like a B-spline? What if I take a triangular function? And there is one statement that is easy to make, that you can take any S0 function. It's not a good way of introducing the space to say, I define S0 as the space of all the functions where you can find one function in the space that you want to define and so on. So therefore it's good to say, I take a particular one. But just as an exercise related to my explanation of amalgam spaces, I've told you it's very close to the idea of cutting into pieces. So I take a definition and say I cut out with a big plateau function. Now you're coming and say, well, what if I do the same thing with a smaller plateau function? So kind of compress everything twice the length, half the length. It's clear that I will have to move it in a more dense way, but kind of instead of having large pieces, I have twice as many small pieces or so. Then the first thing is, can I control what's happening in the half of this? Well, you're multiplying something that you can control with something in an algebra. Multiplication controlled with this, they all have the same norm, these little cutout functions. You control the small pieces. Well, there are twice as many, so you have a constant coming in the multiplicity. Now, opposite direction, somebody says, I have measured things with small partition of unity. Now I say, well, that's musically not relevant, I need a long window. I'm willing to take larger jumps. Well, you're saying, well, the length is now 5 times the length of the original one. So you have to add 5 times and another 5 times. Well, whether you have now 5 copies or 5 infinite series or so you add up, it's a constant, it's just finite dimensional stuff. We actually have developed, this was one of my PhD students who had this idea, what we call disjointization principle. So somehow assume you have this partition of unity which is overlapping, and we have seen cutting is not a good idea, overlapping is necessary. So we do it with L2 and then they are overlapping, so the pieces are not orthogonal. And there the following trick helps a lot. Assume again we have a partition of unity of these building blocks. Maybe also produce a slide next time. Then the idea is this one is overlapping with its neighbor, left and right. But maybe not, if I do it a good job, it's not overlapping with the second one. So I can take all the labels which have even numbers. And all the things which are happening here are perpendicular to each other. So if I have the L2 norm of the sequence of the pieces, by just we have orthogonal things in the Hilbert space, the L2 norm of the pieces in the Hilbert space norm will tell me what the L2 norm is, Pythagoras. The same will be for those in the odd numbers, 1, 3, 5, 7. So if we have an infinite sum, and that's usually the problem, but we can split it and we have 2 slightly overlapping spaces, but within every of these spaces we have an orthonormal basis which has no problem, which is exact orthogonal, then you can say it's weakly orthogonal or so. And the same thing can be done with LP norms or so. That's really the situation that we encounter very much in this situation. So Gabor thinks they are always a little bit overlapping, so you never can say it's just exact orthogonality. The main point is to organize these structures so that you can say we split into finitely infinite families. Within each family everything is fine, and because it's only finitely many families, we can work quite well with these things. So we have called this the disjointization principle, and I think that's an important idea. Now let's see, there may be just one general outlook on how it goes on with the Gabor stuff or so. I think I have this extra slide in MATLAB. Yeah. So again, kind of a mixture of discrete computations and continuous explanation or so. Here I have created a band-limited function, which is meaning a trigonometric polynomial with maximal frequency, distance from the center, and positive and negative frequencies. But you can take it as this would be a recording. Somebody has recorded. He's not, the bed would be here with ultrasound or so, but you have recorded up to 20 kilohertz, but for a long time or so. That's kind of what the spectrogram would tell you. Or you have an analog telephone line with maximal frequency 3000 hertz, it would be something like this. So in a continuous setting, you're producing a lot of coefficients, color products with this, and they make up this spectrogram. So the first thing is, can you recover from the spectrogram? And we've seen the VG star is a continuous way of doing it. And now, so to say, the idea of Gabor was, if we have this continuous setting, try to make this lattice such that we have the analog of Shannon theorem, that we are not too sparse, because if you take a big lattice with large lattice constants, you might have signals which are having sampling values in the spectrogram and you are still not having a signal. On the other hand, if you would take it too dense, then it's having linear dependencies and it would be no uniqueness. And my argument nowadays is, he was hoping that at the critical lattice Gauss function with integer time frequency shifts, he has a system which is okay and respaces in the modern terminology. And he did not realize that he is actually losing both properties. If you discuss it at length, you don't have a linear independent system because the ±1 pattern gives you a convergent thing in the distributional sense which represents 0, and you're not getting everything with L2 coefficients. Even bounded coefficients don't give you everything. So you have to make a decision whether your lattice should be a little bit redundant. In our discrete setting, it means my lattice has to have more than n building blocks. We have seen this example, critical density is missing out one dimension or so. Or you say, I want to do mobile communication. That's our other application. I want to send pulses. I want to communicate with you by playing music to you. So assume you are all Mozart, and I am playing a piece of Haydn, which was before Mozart, and you would say, oh, I can find out. He was playing this accord, and actually the C was that amplitude, and the E and the G, and so on. So instead of Morse long short binary thing, we would have harmonic things, and because we're having classical music, we have one accord, another accord, another accord. Some distance in time, some resolution, separation, frequency. So I would say I build a Gabor sum, and we look at the spectrogram, things having some separation. And at one point I was this idea, one can really prove that Gabor families with lattice constants which are large enough are actually respaces. So if somebody is giving you a linear combination, you can recover the coefficients, even if it's infinitely many or so. And I was at that time studying these Gabor things, and I was then calling it the piano reconstruction theorem, exactly in this spirit of Mozart was able to go to the Sixtinian chapel. They had a secret choir, kind of, it was so good that nobody should see the score, nobody should be able to sing that choir outside of the chapel or so. So this was secret music, so to say. At the time, no recording, nothing else. So Mozart was allowed, as I think a young man, to listen to this, and he went out and he wrote down the score. Yes, of course, he's a genius who was very well trained, but there was a physical substance to it. So we could have taken a recorder at that, and we could play it into the gaborator, and the machine would tell us, well, take the notes from the gaborator. So somehow, what is the basis? Well, this is not arbitrary signals. It's not noise, so to say. It's well separated in time and frequency. And if you know it, you can try to recover it. So if you would do something like this, you would look at the spectrogram. And you would say, well, maybe it's a collection of bump functions. So just think of a two-dimensional situation where somebody would put in the plane a lot of 2D Gauss functions. And that's an area with some hills and some mountains or so. And then you see a big mountain here, and you would say, okay, the height is 5.7 or so. Maybe the coefficient is 5.7. And then you say, well, this is my first guess. So you build a landscape with the height of all these peaks. You identify the peaks because they're sufficiently separated. And then you are saying, this is my first reconstruction. And you find out this guess was not, you get something like 6.1. And say, well, I have to do a correction. So you are subtracting something because you would like to have 5.7. The tails of the neighboring Gauss functions were contributing a little bit. So you have had too much altogether. So you're subtracting a little bit, and you continue like this. I would say what you're doing mathematically, you have a system of equation, but it's diagonal dominant. You have a good approximation of the right term at the right place, but the others are destroying a little bit. But each iteration of this is like a Neumann series representation that we've seen to invert within any Banach algebra. Now in the matrix algebra, diagonal dominant matrices can be done. So essentially my so-called piano reconstruction theorem is nothing else. If somebody is giving you sound signals which have a minimal separation, so you see blobs here and there, so then this harmless trick of saying, well, try the amplitude, try as a coefficient the first one, and then iterate, and I have to write down the details, but essentially you're having a invertible matrix which is diagonal dominant, and that's all I need. So it's clear that first of all, if you have a coarse lattice undersampling, you will have to give up on representing arbitrary signals, but it's very good to communicate. We can ask our mobile provider to send us linear combinations of Gauss functions. They will be a little smeared or so, they will be a little bit distorted, but you can retrieve the coefficients, which are after all binary. Our project with the engineers was essentially, they say they are almost eigenvectors, so if they are eigenvectors and there is a fading factor, you compensate the fading. And we were saying, patent number 1, no, it's a little bit of a twist. Let's try to find out what the twist is, because if we know the distortion, we can correct for the distortion. And then we know what the distortion is, we have still to correct it. So the mobile phone has to be able, in principle, logically at least, to do the inversion of the matrix in an approximate way. So these were the 2 patents that we still have, and I don't think they will be really can be converted into any money or so. But the point is, it's mathematically relevant what was doing, because this situation from mobile station to the mobile phone or so is really a slowly varying channel. It would be unrealistic to say it's just a convolution operator. That's true if you're on your balcony, you have direct line of sight, as it is called, to your station, and it's sending no interruption. You receive a signal, the wave sent out is received more or less undisturbed or so. But if you're already in the room, it's the reflections of the electromagnetic wave which give a smearing. And if I go to the other end of the corner, you all know this. At this corner you have a good connection, at the other corner you have a bad connection. So the smearing must be different. One must be more difficult than the other. And of course you do not compute the reflections of all these symbols, but you know it has to be some smearing, and that has to be accounted for. So in that sense you have, we can use both sides of Gabor analysis, the density to represent signals and the other one to have communication. And actually for one of my coworkers, Werner Kotzek, this was actually giving him a job. So we were working on Gabor analysis, it's in our book on Gabor analysis. And then he was hired by Siemens to start to work on the ADSL, which at that time was a new development, which is asynchronous digital server line. So nowadays it's quite standard or so. You would like to connect with your server or so, but of course you hope that downloading is fast, because that's what you do most of the time, but you also can upload your images to the cloud or so. And that doesn't have to be at the same speed, because the server is just kind of one. There are many users, and he can download quickly or so. So you need some communication patterns or so. And if you have a communication channel, then having a highly packed channel is good. So if you have Gabor systems, a lattice which is very far apart, as I said with the piano reconstruction, that's easy to use, but it's not extremely efficient. You would like to go higher density. If you take too many density, then it's spoiled. It's kind of a room with a lot of noise, and you cannot hear anything anymore. And there is a principle that we will discuss a little bit later, which says that these 2 independent questions are mathematically actually equivalent. So because he was trained in one side, using the equivalence, he could work on the other side with the same machinery, more or less. And that's something I think I can do tomorrow in the practical part again, if I think we have it, and then discuss theoretically in the afternoon. Thank you very much.